Hello and welcome back to Introductory Electromancy. In this episode we will discuss inductors. What is an inductor? Well, you will recall from the previous episode that a capacitor stores energy in an electrostatic field between two plates. An inductor stores energy in a magnetic field. It is possible that at some point earlier in school you did an experiment where you took an iron-containing nail and wrapped wire around it. Then connected the wire to some sort of power source and observed that it became possible to pick up paper clips and various other small ferrous objects with the nail. Your teacher at the time might have mentioned that this is because you were causing the nail to become magnetic, a process known as electromagnetism. You may even have seen drawings of magnetic field lines resulting from the current flowing through this ferrous nail, which you wrapped wire around and then ran a current through the wire. It is this magnetic field that is responsible for storing the energy in an inductor. An inductor is usually given the letter L as opposed to C for a capacitor and R for a resistor. This is the symbol for an air core inductor, and different things are put next to the squiggle depending on what type of core the inductor uses. In your basic electromagnet nail experiment, it would be an iron core inductor. This is the symbol for a laminated iron core inductor. And dashed lines are used for ferrite core inductors. However, in most applications, schematics, you'll just see this as a stand-in for every kind of inductor. Just a line and some beautiful little squiggles. Now, I have physical inductors here, but I have not yet done the prep work to make them usable for a good practical experiment, because these have such short time constants that you won't be able to see something like an LED slowly dimming. But how this inductor works, how any inductor works, some coil of wire. This coil of wire may be wrapped around a material such as iron or ferrite that concentrates the magnetic field, but let's not worry about that right now. You run a current through it. It causes the wire coil to develop a magnetic field. Now, at the time that this magnetic field is forming, these field lines have to pop out through the coil of wire. Anytime you move a magnetic field line across a piece of wire, you induce a corresponding voltage and current in the wire. These magnetic field lines popping out through the coil of the inductor generate an opposition to change in current through the inductor. This might be a case where the hydraulic analogy is useful. So, we have already talked about how a pump is somewhat analogous to a battery, and how the flow rate of water is somewhat analogous to current, and the pressure of water is somewhat analogous to voltage. So in this example, a wire would be a pipe, the pump would be your battery. A resistor would be something like a piece of pipe that has a narrow restriction, something that would slow down the rate of flow of water. A switch would be an on-off valve. And so on and so forth. Now, for our new recently added components, a capacitor would be something akin to a tank separated by a flexible membrane. In the middle. Applying water pressure would cause the membrane to flex, and then removing it, the inner membrane would want to flex back. Now, an inductor is something akin to a weighted impeller. That is, an impeller in the pipe that is not connected to anything, but is heavy. So water flow will initially be impeded by the impeller, but as water flows, it will spin up. And then if you try to stop the flow of water, because it's already spinning, it will continue to push the water. This is an approximate analogy, but it results from a magnetic field which pops out as current flow is increased. The action of the magnetic field popping out and cutting across the wires generates an opposing voltage to the one that is pushing the current flow. But then, once the magnetic field is developed, that is, it's fully popped out of the coils of wire and exists around the entire solenoid coil, if you try to open the circuit and stop the flow of current, the magnetic field collapses. The collapse of the magnetic field causes its field lines to cut across the windings of the inductor, generating a positive voltage spike, trying to keep the same amount of current flowing. A capacitor tries to keep voltage constant. An inductor tries to keep current constant. The easiest way to demonstrate this physically, which I am trying to do on your behalf, dear viewer, because as much as we all love dry lectures, well, it's nice to see these principles in action. I'm going to take this inductor here, and I'm going to use it to short circuit the battery. Then, when I pull one lead of it off of the battery, it should create a spark at that lead. Because what's happening is I connect it, I short circuit the battery, current begins flowing through the inductor, conventional current flows out of the plus terminal into the minus, and then that causes a magnetic field to develop in these windings here. The ferrite core exists to concentrate the magnetic field. This increases the effective inductance for a given number and size of windings. So I short the battery, current flows, a magnetic field appears here. I leave it shorted for long enough so that the action of the magnetic field popping out, cutting across the wires and producing a back EMF is reduced to almost zero. Then when I suddenly disconnect it, the magnetic field that has accumulated collapses, those field lines collapsing and cutting across these wires induce a huge voltage spike, which is enough to break down the resistance of air. It breaks down the air because in regular air, the electrons are all bound in mostly diatomic oxygen and nitrogen. But if you put enough voltage across it, you can free the electrons from these atoms, creating a plasma. So here goes. You can hear a little crackle, but it's hard to see the spark. The very tiniest spark. That spark is the collapse of the magnetic field of the inductor. It occurs when I pull the lead off of the battery terminal. Now, using something like a diode, you can harvest the energy of that spark and shunt it over into something like a capacitor, which lets you store it. And so you have a circuit that effectively repeatedly shorts a battery through an inductor, then directs the spark away from the short with a diode, stores it in a capacitor, and this lets you convert a lower voltage up to a higher one. It's called a boost converter. It's the sort of thing we can get into more detail regarding a bit later. In any case, this is about how far we've built up in our understanding. We have our pump, which is our battery or other voltage source, our resistor, which is some sort of restriction, an opposition to flow, a capacitor, which we're considering hydraulically as a large tank with a flexible membrane in the middle of it, and an inductor, which we're considering as a piece of pipe with a weighted impeller in it. Now, for you, dear viewer, you might not have immediate access to all of these parts. You might be doing this using only a phone as your key available resource, and budget for parts is an issue. I have accumulated these parts over a long period of time. I believe I set these boxes up when I was 15, and now I'm 34. So, for the viewer who does not have all of these materials readily at hand, simulations are useful. Simulation software. You can spend money on simulation software, but I don't really recommend that you do so. I have, for class requirements in the past, been compelled to purchase Multisim. It's not that great. Now, this simulator, which I will link in the description, falstad.com/circuit, this is an in-browser simulator that lets you simulate a wide variety of different circuits. You don't have to install anything, you just need a web browser that can get to it. So you should be able to do this even with only just a phone without even needing a computer. I haven't tested it on my phone. I probably should have done that before recording this, but here we are. The circuit that is being simulated here is called an RCL circuit, resistor, capacitor, inductor. And it has the effect of swishing charge back and forth. Assuming you start with the capacitor charged, the capacitor discharges through the resistor and inductor. That creates a magnetic field here. Once the capacitor's charge is equalized, this inductor is used to a certain amount of current flowing, and it wants to keep that current flowing, so its magnetic field collapses, which induces a voltage which causes this right-hand side of the capacitor to become charged. And this continues until this magnetic field has fully collapsed. Then this side is charged, then it starts conducting the other way, building up a magnetic field here. And in this example, you can see that the rate of change is slowing down. That's due to the damping effect of this resistor here. The LC circuit, inductor capacitor, is a common form of oscillator that produces a clean sine wave by shuffling energy back and forth. between being stored electrostatically and in the form of a magnetic field here in the inductor. In any case, I'll be linking to this in the description, and then another useful resource is a program called LTspice. Originally, I think it stood for Linear Technology Spice, but now it is from Analog Devices. It is an on-simulator, or an on-computer simulator that is somewhat more advanced than the browser-based falstad one, and it is free. This is important. They list downloads for Windows and Mac OS, but I have also gotten it working in Linux using Wine, W-I-N-E. I think it stands for Windows in Native Environment. It's a compatibility layer that lets you run Windows programs on Linux. But yes, LTspice is free, but it requires a computer. Falstad Circuit Simulator applet is free and can be done in the browser on a phone, as far as I understand. This has been your introduction to inductors. Now, interesting things happen if you wind two sets of wires on the same magnetic core, but we'll have to get into that later. Thank you. Have a good day.